Hey everyone, welcome to The Explainer. Today, we're uncovering the hidden magic that literally powers nearly every piece of tech you interact with on a daily basis. I mean, have you ever actually stopped to think about how the software on your devices gets made? We all interact with these perfectly finished apps and operating systems, but there is an entire invisible foundation of engineering happening way before that code ever reaches your screen. And honestly, understanding this foundation, it unlocks a huge part of how modern software engineering actually works.
Okay, let's dive right into this. At first glance, it sounds kind of like a paradox. How does software that's built on a massive, super powerful Intel server end up running flawlessly on a tiny ARM-based smartphone? Or, a smart TV? Or a drone? These are fundamentally different pieces of hardware. They just don't operate the same way. So how in the world does the software industry solve this massive hardware divide? Well, to answer that, we really have to look at how software is born in the first place.
You see, it all starts with compilation. We write our software in human-readable languages. Think C, C++, Rust, or Go. But CPUs? They don't understand any of that. They only understand raw machine instructions. So we have to rely on compilers like GCC or Clang to convert that source code into an executable binary. But here's the catch. It is absolutely not a universal translation. And that's because different devices use entirely different CPU architectures. Most of our standard desktops and laptops run on x86_64. But smartphones, Raspberry Pis, embedded devices, they rely heavily on ARM architectures. You can kind of think of these like completely different spoken languages. An Intel chip literally cannot understand the internal instruction language of an ARM chip, period. If you compile software for x86, there's just no way it's going to run on ARM. Which brings us to our first major concept, the native build environment. This is the direct approach, and it's probably how you first learned to program on your personal laptop. In a native build, the machine compiling the software and the machine running the software are the exact same architecture. You write your code on your AMD 64 laptop, you compile it, you get an AMD 64 binary out, and boom, you run it right there. It's this beautifully simple, closed loop.
That up. Imagine a company building software for phones, smart TVs, cloud servers, routers, and IoT devices. If they only relied on native builds, they'd have to maintain separate physical systems and hardware test labs for every single one of those architectures. Imagine literally needing rows and rows of x86 servers, ARM servers, RISC-V systems, and custom embedded boards just to compile your daily code. It's incredibly expensive, and frankly, it just doesn't scale.
And that massive scaling headache brings us to Section 1, the cross-build environment. One powerful machine building for many architectures. So instead of building directly on target hardware, what if one really powerful machine acted as a factory? Now, what's really interesting about this process is the specific tool that makes it happen. Take a look at arch64.linux-gnu.gcc. Now, I know that looks like a jumbled file name, but it's actually a cross-compiler. It runs perfectly fine on your standard x86 system, but, and here's the magic, it knows exactly how to generate binaries for an entirely different CPU architecture, like ARM.
Because of that, the entire workflow just totally shifts. We start on our heavy-duty AMD 64 machine, we feed our source code into the ARM cross-compiler, and out pops an ARM 64 binary that is totally ready to ship to the target device. By decoupling the build machine from the target device, we solve the hardware scaling issue overnight. You can literally have one massive cloud server just farming out builds for a dozen totally different devices.
Now, I don't want to make this sound like a flawless magic bullet because it definitely introduces a serious under-the-hood challenge. Cross-compilation is notoriously complex. Think about it. Your software doesn't just float around in a vacuum. It relies on libraries, headers, linkers, all these runtime dependencies. And every single one of these puzzle pieces has to perfectly match the target architecture. If you accidentally try to link an ARM 64 build against an AMD 64 library that's just sitting there on your build machine, yeah, the entire software build breaks instantly.
So how do we manage all this chaos?
Well, modern operating systems introduced multi-arch systems. Take an Ubuntu machine, for example. It actually allows libraries from entirely different architectures to live on the exact same server at the exact same time. They're just safely tucked away in their own separate directories. This way, when your cross-compiler goes hunting for a piece of code to link, you can point it exclusively to the ARM 64 directory, completely ignoring the host machine's AMD 64 files. It keeps everything neat and separated.
Okay, but even with multi-arch, things can still go sideways. Let me walk you through a classic nightmare scenario for build engineers. It's known as the helper tool trap. Imagine your build process is so complex that it needs to quickly generate a temporary tool, maybe like a metadata parser, just to help finish the compilation. The AMD 64 build machine creates this helper tool, but because its brain is completely in cross-compiling mode, it accidentally builds that helper tool for ARM64. And so, what happens when an AMD 64 machine tries to actually execute the ARM binary it just created? Boom, you get hit with a fatal error, XX format error. The build totally crashes. Your host machine is basically throwing its hands up and saying, I have absolutely no idea what language this file is speaking. Navigating these highly specific, super technical traps, that is exactly why cross-platform engineering is considered such an elite skill.
Which neatly brings us to Section 2, Emulation and QEMU, smoothing out those architecture execution problems.
So when you actually do need to run that ARM binary on your AMD 64 machine just to get the build finished, emulation tools like QEMU swoop in to save the day. QEMU basically translates those architectures on the fly. And honestly, this invisible infrastructure is literally everywhere. It powers Android development, embedded Linux, those gigantic Ubuntu and Debian build farms, even cloud-native Docker containers, and Apple's massive transition to Apple Silicon. It really is the true connective tissue of the tech world. And this brilliantly illustrates the final core trade-off that every software engineer has to balance, right? Native builds are simple. They're straightforward, they're way easier to debug, but they lock you into requiring exactly matching hardware. Cross builds, on the other hand, offer this incredible scalability, efficiency, and flexibility. But of course, they invite all the ghosts of complex dependencies and toolchain traps right into your workflow. Truth is, both are absolutely essential to the modern tech stack.
Which really leaves us with this final thought. Cross-compilation has served as this incredible, invisible bridge uniting a wildly fragmented hardware landscape. It lets a single standard server breathe life into everything from smartwatches to drones to massive cloud systems. So as brand new, wildly different CPU architectures emerge over the next few years, what impossible multi-platform devices are software engineers going to connect next?